Okay, the next set of or the next group, Charlie, we talk about more about filters, oscillators, and receivers and transmitters. This will represent one more question on the test. So this applies to not just RF filters, basically any kind of filter, although I guess they defined RF as anything above DC, so still consistent. You essentially have two kinds, low pass filters and high pass filters, where a low pass will pass everything below what they call a cutoff frequency or half power point. The high pass will pass all frequencies above that. If you put these two together, you can make a band pass or a band stop. Sometimes we call this a notch filter for a band stop. So if I was to take this high pass filter and adjust it so its cutoff frequency was down here lower than the cutoff frequency of the low pass, just move this over here, I've got a bandpass filter. So it's going to pass everything in this pass band. Likewise, if I shift them the other way, I have a band stop filter, so it's going to pass everything below and everything above that particular frequency band. So for a low pass filter, okay, it has a cutoff frequency that is at what they call the 3 dB point, minus 3 dB point, or half power. So the signal is one half of the input signal coming through its passband. If it's a typical first order filter, you're going to have a slope when it starts to attenuate of 20 dB per decade. So that means that as frequency goes up in tens, you're going to drop 20 dB. So if this was, say, 100 hertz at this point, when I got to 1,000 hertz, it's going to be 20 dB lower. When I got to 10,000 hertz, it's going to be another 20 dB. If I do this with more than a first order, okay, that slope increases by 2 or 3 or 4. So you can get some very steep skirts for higher order filters, which have more LC components in. The key thing, though, is the cutoff frequency, and that the impedance, it needs to be designed so it's working at the impedance it's connected to. Like in the case of, if this was a output for a transmitter going into a 50 ohm feed line, you'd want to design that filter so it works at 50 ohms. The green part here is called the pass band. So that's anything from 0 up to whatever the cutoff frequency is. So what is the frequency above which a low pass filter's output power is less than half the input power? Okay, bandpass. We're going to skip the high pass. In the bandpass, like I said, it's just a combination of a high pass and a low pass filter. So it has two cutoff frequencies. It has the lower cutoff frequency, so it passes everything above the lower cutoff. It has a higher cutoff, so it attenuates everything above the upper cutoff. And they're both half power points. They don't get into it, but another thing is you get a phase shift because these are reactive components. So it turns out that at the half power points, the phase shift of the signal coming out is 45 degrees. It doesn't quite, these two charts aren't quite synced up, but this point down here would actually be at 45. Okay, so we also have a term called ultimate rejection, and that signifies the filter's ability to reject signals outside its passband. So its ultimate rejection would be in this region above it or this region below it for the bandpass filter. And it would be determined by how steep these slopes are. So how many dB down the signal would be when it's out of the passband. Now there's also insertion loss. If these are passive filters, then you don't get out what you put into it. There'd be some loss. And that's what we call insertion loss. Even though here they're showing it at 0 dB, that's not really relative to the input signal. It's just relative to the pass band of the filter. So you may have 1 or 2, 3 dB insertion loss on the filter, which is another reason why a lot of times they will use active filters. So they actually have active components, amplifiers in them to compensate for the loss.
So when ultimate rejection, you're saying anything outside the 3 dB point?
Right. The bandwidth of a bandpass filter is measured between what two frequencies?
Upper and lower.
All right. What term specifies a filter's attenuation inside its passband?
Oh.
You paid attention.
Usually, yeah.
What determines a filter's ability to reject signals outside its passband?
Oh, delta. Paying attention there again.
Okay. Receivers and transmitters. Not sure why he started with SSB, but for a single sideband transmitter or receiver, you're using in this case of the block diagram, we got a transmitter down here. Turn my pointer back on. So we have our audio signal, okay, usually coming from a person speaking into a microphone. You may have some form of amplification for it, so you can control the gain on the microphone. It could go into a speech processing circuit called a compressor, where you can actually kind of shift the frequency characteristics of the audio signal to move more of the power up into the higher frequency part. So it gets a little better modulation. We also have the carrier oscillator, which is the frequency that we're going to operate or transmit at. And we feed those into what's called a balanced modulator. And the reason it's different than a regular modulator is that it suppresses the carrier. If it was a normal modulator, your output would be the sum and difference of the carrier and the audio signal plus the carrier would be through at twice. You'd have two F sub Cs. In a balanced modulator, it cancels the carriers out, so you only have the two sidebands coming out of it. So you've already suppressed the carrier by using a balanced modulator. You run that through a filter, okay? So whether you're going to be upper sideband or lower sideband, you're going to filter the one you don't want out and only let through, let's say in this case, the upper sideband. Now that I've got that, I'm going to mix it with this other local oscillator to shift its frequency, and then it goes to the power stage, and that's what you transmit. So you're only going to send out one sideband, no carrier, no lower sideband or opposite sideband. Here's what a typical balanced modulator looks like. And you can normally get these as a package circuit. I know many circuit labs used to make these. These for some like a bunch to a pack or something. Oh, probably. You can get anything on Amazon, but I guess Mini Circuits is still in business. I don't know. This was from a long time ago, but
I keep getting emails from Jamco.
oh, okay, yeah. It's basically a ring diode network between two center tap transformers, and won't go through all the details, but that's how it cancels out the carrier so that you just get the two sidebands out. So it's the difference between the modulating frequency and the carrier, either plus or minus. So one sideband will be higher than the suppressed carrier, the other one will be lower. Also, the lower one is inverted frequency-wise. So the higher frequency of the voice is going to be on the bottom end because of the subtraction. Okay, what output is produced by a balanced modulator?
Not upside band.
Right. Double sideband, no carrier. What circuit is used to select one of the sidebands from a balanced modulator? So how do we get rid of a sideband?
Alpha.
How do we get rid of a sideband? What do you do when you want to get rid of something?
Filter that. All
right, filter it. Okay. And that's a single sideband receiver. Kind of works opposite. The basic difference, what they're pointing out is for single sideband, you can't use a normal envelope detector, which probably comes up on a later chart of what the envelope of the modulated waveform is. And that represents the amplitude modulation signal or audio signal. It doesn't work for single sideband, so you have to use what they call a product detector, which is the product of these two signals, the IF signal, which is your upper or lower sideband signal, shifted up at your IF frequency.
With the beat frequency oscillator.
With the beat frequency oscillator to offset it from your IF frequency back to audio. So, but the key thing is that it requires a product detector for a single sideband. So when you have a multi-mode transceiver, okay, you've got to have the ability to switch in filters to filter upper and lower sideband. You've got to be able to switch different detectors and demodulators. You want a discriminator if you're doing FM. You got to switch in a product detector for single sideband. You can use a regular envelope detector, a simple mixer if it's AM. So you've got to switch all those things around depending on which mode you want to operate in. If you've got a multi-mode, which most of them are, except for Viron's QRPs, they're probably single mode.
I wasn't paying attention. That's during.
Does your QRP do anything besides single sideband and CW?
Oh, it does everything.
Oh, okay. Well,
Yeah,
so you got a multi-mode QRP transceiver.
I be shacking the box that does everything all the time.
Okay.
That's the only way to go when you're in a condo in Florida.
Okay.
You want a Swiss Army knife.
Right. All right. This one just shows the suppressed carrier and one of the sidebands that was filtered out. So you're only seeing in this case the upper sideband. And that's where all your voice information is in this. Now, in this particular one, the way they've drawn it, most of your modulating power is down here on the lower frequencies. And so that's one of the things that you would change with a compressor is kind of changing the shape of that curve a little bit. So how is a product detector used?
Gee,
It's about the only time it's required for single sideband.
yeah.
Okay, super heterodyne. Most of the modern transceivers or receivers are going to be a super heterodyne configuration where you're going to heterodyne the signal. So you have an RF signal coming in, you mix it with a local oscillator and convert it to normally a lower intermediate frequency. That's called heterodyning. I think the term super heterodyne came about because they would normally have, at least for the higher end radios, more than one conversion state or IF. So you'd convert it to a higher frequency IF and then convert it again down to a lower frequency. And it made it easier to amplify and filter the intermediate frequencies. And then at the end, you're going to demodulate it or product detect it or discriminate it, depending on what mode it's operating in.
And Jason still uses a lot of that in their higher end stuff.
What does?
Jason.
Oh, yeah. Well, even when we get to SDR radios, the blocks shown are basically the same. It's just that you're going to do most of it digitally in a digital signal processor. Well, anything you can describe mathematically, you can basically do in a software-defined radio digitally, which is why you can do some amazing things. There's no way you can do them with analog circuits.
Love our SDR.
In this case, we use the mixer, okay, to convert your RF input signal along with whatever your local oscillator is into an intermediate frequency. Now, the local oscillator also a lot of times called VFO, variable frequency oscillator, is actually what you're tuning when you tune a signal in. Because this signal that you want is a fixed frequency. And your intermediate frequency filters and amplifiers are operating at a fixed frequency, say 455 kilohertz, which is kind of a typical one. So you want your local oscillator to be offset from the frequency you're trying to receive by whatever that intermediate frequency is, either above it, or below it, depending on whether you want to shift up or shift down. And then after the intermediate frequency, and we filter it and we amplify it, you'll have some bandpass filters in here because you want to get rid of everything that's outside of the pass band of the IF. And then we demodulate it to convert it back into an audio signal. In the case of an FM receiver, the front end is basically the same. The IF strip is basically the same, with the exception that we're getting a frequency modulated signal that has constant amplitude. Whereas in the previous one with an AM signal, we're amplifying the amplitude of the signal. So they have typically a circuit called a limiter in an FM receiver to limit the amplitude of the IF signal, because it turns out some discriminators are sensitive to amplitude modulation. So all you want to get out is the frequency deviation. So you want to get rid of any amplitude modulation or noise that's on there. So that's the purpose of the limiter circuit. So it's kind of like an ALC circuit. And we have a thing here called de-emphasis. Normally on an FM transmitter, there'll be a what they call an emphasis circuit, which is kind of like the voice compressor, and it will change the frequency range of the voice signal. And I don't remember all the reasons why, but when you get to the receiver, you have to undo that. And that's what the de-emphasis circuit does.
If you're transmitting and changing between narrow band and wide band, I can imagine that would have to be different also.
Oh yeah, a lot of this stuff has to change depending on the mode. And then we finally get it back to an audio signal and comes out your headphones, your speaker, whatever. The key here is that the discriminator for it's called a discriminator in FM because it's sensitive to frequency changes. It's like on the transmitter end, we use a reactance modulator that will allow us to change the frequency with varying voltage. So one of the most important receiver specifications is the sensitivity. Another one, which I think is coming up, is selectivity. But as far as sensitivity, it's how well your receiver can receive weak signals. So it's partly how low the noise floor is on the receiver itself, okay, in addition to whatever noise you're picking up, and how much gain you have to amplify the signal. In some cases, your transceiver may have some preamplifiers that you can put in the front end to get increased gain besides what you do with your normal input amplifier. Let's see. So some of the things that affect it are your input amplifier gain, the demodulator bandwidth, and the input amplifier noise figure. So those are really the three things that determine the sensitivity of the receiver. Those you need to remember. It's coming up shortly. And that the ability to receive weak signals is part of sensitivity. So what parameters affect receiver sensitivity? It's our first one of the day. All these choices are correct. Okay. Direct digital synthesizers. In analog radios, the VFO, or local oscillator, variable frequency oscillator, are just linear analog tuned circuits to generate a particular frequency signal. You control the oscillator by changing normally the capacitor in the tuned circuit of the oscillator. When we go to the digital domain, okay, we can generate that variable frequency digitally and get the advantage of having it just because it's based on a crystal oscillator. So it has the stability of a crystal oscillator, where a normal analog tuned circuit will drift with temperature and other, voltage variations and things, which a lot of times they will try to generate it with a crystal oscillator and vary the crystal frequency a little bit. So a direct digital synthesizer has the stability of a crystal oscillator, but it's still a variable frequency over a wide range.
You don't have to buy hundreds of crystals.
And you don't have to buy different crystals, right? So that's becoming much more common in modern radios, is to do a direct digital synthesis of your VFO signal or local oscillator signal. This is one of the typical integrated
waveform issues. It was talking about the PSK and yeah.
Oh, did it?
Yeah.
Yeah. It can also put out not just a sine wave, but typically they can generate square waves, saw waves. You can do phase shift keying and frequency shift keying with them, where you're synthesizing the output frequency. So you can do a jump from a mark and a space frequency, or like in FT8, where you've got 8 different tones you're generating that are offset. This is a typical little integrated circuit that does all this stuff in this little 12-pin, 10-pin package. And it has this first stage, which they call a phase accumulator, fed by a high frequency clock. And in there, what you're doing is determining how many samples of the sine wave you're trying to generate. So let's say that clock signal was 360 times the frequency that you wanted to generate. So every one of those clock samples is going to be 1 degree of phase of that sine wave. So I feed that into a read-only memory, which is just has a table in it, and for every degree, okay, it's got the equivalent digital value of that sine wave. So as I step through that, okay, the output that I'm seeing are the digital samples or representations of the sine wave. And then I feed it through a digital to analog converter. So I'm basically converting those digital samples back into a sine wave and putting a low pass filter to get rid of all the high frequency stuff. So I've got a sine wave on the output that was done by just a lookup table essentially in that ROM.
You're just sampling the wave rather than being.
Right. The samples are stored in there for many different amounts of phase. And then the clock signal is going to be some multiple of or samples of your sine wave times whatever your output frequency needs to be that you want. So which of the following is characteristic of a direct digital synthesizer?
Delta.
All right. VFO with it looks like a crystal oscillator. Okay. SDRs, called a software-defined radio. And what we do is, if you remember that block diagram for the superheterodyne, we're basically going to implement that with software in normally a digital signal processing chip and maybe some grid array, which are big integrated circuits with a lot of components. In this particular one, okay, we're showing a low noise amplifier on the receiver input, and it's feeding two different mixers. One of those has a 90-degree phase shift, and we call these two outputs I and Q. I can't tell you where I and Q came from, but I think the Q stands for quadrature, which means it's 90 degrees out of phase with the other one. We run that through some filtering and through an analog to digital converter, and we feed that into the processing portion. So we have two samples of the RF signal that were shifted in frequency by the local oscillator, which was another direct digital synthesizer. And now we can play with those two signals, one 90 degrees out of phase with the other one, and do all these mathematical things with them and output data, which we convert back to an audio signal by going through the digital analog converter and then a filter. The similar process for the transmitter, where we do all of the processing and output in digital form, whatever waveform that we want. So if we're generating a single sideband signal, we're going to synthesize digitally what that waveform needs to be and run that through a digital analog. So we'll get a sine wave out of there, which I can combine the I and Q and actually wind up with an RF sine wave, which is only the sideband at whatever frequency we're transmitting. So the only analog circuitry is whatever's in the front end, and sometimes even these parts are done digitally, where it's almost a direct input from the antenna into an analog to digital converter. So most of the processing, or almost all of it, depending on the manufacturer, is done in software. It's actually more like firmware. You use I and Q signals, which have a 90 degrees phase difference. So it's the same signal, just shifted in phase. And you can essentially generate any kind of modulation or demodulation or filtering that you can represent mathematically. If you can write the equations for it, you can generate it. So which of these functions is performed by software in a software-defined radio? Our second one of the day. What is an advantage of using I and Q signals in software-defined radios?
I'm eliminating.
Okay, read them all. Which ones can you throw out?
No problem. I'm leaning towards Bravo. Okay, I'll go with Bravo.
So it doesn't eliminate the need for analog to digital converters. Okay.
Right. It's doing that itself.
They might be included in the DSP circuitry, and they may be external, like that block diagram showed. But you still have to do that function, converting analog to digital, in order to play with it in the digital world. It doesn't have anything to do with minimum detectable signal level, because remember that was the same as receiver sensitivity, and it depended on your input gain, your demodulator noise, and whatever the third one was. So none of those. And I don't know about automatic conversion from digital to analog. That's not necessarily true, because you will still need, either within the processing portion or separate, a digital to analog converter to get it back to the analog domain for your audio. Digital filters. There will be a lot of those inside the SDR radio. All your bandpass filters, normally you'll have a selection of 3 or more of different bandwidths, and in some cases those are adjustable. A lot of them will have what they call passband tuning, where you actually have 2 bandpass filters and you can shift the cutoff frequencies of the 2 independently and have them overlap and get a very narrow passband, or shift it to one side or the other to eliminate some signal that you don't want coming in. So you can kind of contour the passband so that signal you don't want is outside the passband of your filter. So you can do any of these kinds of shapes or bandwidths. Like I said, if you can represent it mathematically, you can probably do it. Or that's not the case in the analog world. There's limitations on what you can do with filters. And to get very sharp steep skirt filters. You go to 9, 11 stage Chevy Chev and stuff like that, and even some active, where it's much easier to do with a digital filter. Takes a lot of components to do it in the analog world. And then you've got the problem of losses with all of them, stray capacitances and all kinds of intermodulation things. It makes life much simpler, but then there are some downsides to SDRs. Oh, did we lose Amanda? Which of the following is an advantage of a digital signal processing DSP filter compared to an analog filter? What is the phase difference between the I and Q signals that software-defined radio equipment uses for modulation and demodulation? Degrees, quadrature. 1/4 of the waveform, 90 degrees. Okay, it's time for a break.
So this is the camera